Understanding filter design is key to mastering sound systems. With Filter Solution, dive deep into both passive and active filters, explore how they shape frequency responses, and discover the techniques that make them essential in creating the perfect sound. Hi, and welcome to my channel. The first step is to select the filter type. All of these filters are commonly used in real-life crossover designs, but for now, we'll go with Butterwidth. Here, you can choose your desired filter you need, whether it's low pass, high pass, band pass, or band stop. A band stop filter with a very narrow range is known as a notch filter. So, as you can see, all the essential filters are available here. In this video, we'll focus on passive filters. The first assumption we'll make is that the driver has a flat impedance, and all the explanations from this point forward are based on that assumption. If you like, you can watch this to learn how to flatten the impedance response. As you know, our hearing range is roughly between 20 Hz and 20 kHz, so make sure to enter that range into these cells to get meaningful results. Now, let's design a first-order low-pass filter at 1000 Hz. Assume a constant impedance of 4 ohms. Source impedance usually comes from the amplifier, the wiring, and other connections in the system. Set the source resistance to 0 and put 4 ohms here for the load. This is a first-order crossover that uses an inductor based on a constant impedance of 4 ohms. The 4 ohm resistor here represents our constant impedance driver. You can see several curves showing the amplitude, phase, and group delay responses. For a first-order low-pass filter, the amplitude drops by about 6 to 7 decibels per octave. As you know, an octave is twice the cutoff frequency or the filter frequency. 2000 for this example. Let's see what happens with higher orders. For a second-order filter, the slope is 12 decibels per octave. Third order gives 18 decibels, and a fourth order filter reaches 24 decibels per octave. The filter order simply refers to the number of reactive elements, like inductors and capacitors, used in the design. Let's try a high-pass filter. As you know, in a high-pass filter, an octave refers to the point where the frequency is halved. So if the cutoff is at 1000 Hz, 1 octave below would be 500 Hz. 6 decibels per octave for first order, 12 decibels for second order, 18 decibels for third order, and 24 decibels for fourth order filters. Now let's try a bandstop filter. It blocks a specific range and allows frequencies outside that range to pass. The second input here sets the bandwidth. The smaller the bandwidth, the narrower or more focused the notch becomes. Now let's look at a band-pass filter, which is simply a combination of a low-pass and a high-pass filter. Typically, the higher cutoff frequency is around 8 to 10 times greater than the lower cutoff. For example, you can choose to 100 Hz and to 1000 Hz, and the same slope explanations apply here too. While you're paying attention to how the filter order affects the response, it's good to know that this software can really deepen your understanding of filter design. Although it's not free, it's incredibly useful for building accurate filters and can serve as a powerful complement to tools like VituixCAD. Thanks for watching.